Hi everyone, my name is Pamela Franco and I am assistant professor at Universidad de Leiva. I have a PhD in electrical engineering and a master's degree in medical physics. So today I'm going to talk to you about the interpretable machine learning model for characterizing magnetic susceptibility-based biomarkers in first-episode psychosis. So, medical imaging is a cornerstone of modern healthcare. It helps doctors see inside the human body without surgery. Today, let's explore some common imaging modalities and dive into how MRI works. First, there's X-rays, which use radiation to capture images of bones and dense tissues. Then, CT scans combine multiple X-rays images to create cross-sectional views. And ultrasounds, on the other hand, use sound waves to visualize organs and monitor pregnancies. And then we are going to talk about more MRI, or magnetic resonance imaging. So, how this works? So how it works? MRI doesn't use radiation. Instead, it uses strong magnetics and radio waves to create detailed images of the human soft tissue, such as the brain, muscle, and internal organs. Here's how it works. MRI machine generates a powerful magnetic field aligned hydrogen atoms in your body. We use hydrogen because we have biological abundance up to the 60% of the human body is water, and also we have a high hydromagnetic radius. Then the radio waves are sent through, causing this atom to precise. When the radio waves are turned off, the atom releases energy and then realigns with the magnetic field. Special sensors detect this energy and computer process into create highly detailed images. These images help doctors diagnose conditions like tumors, brain injuries, or joint problems with precision. Therefore, medical imaging, and especially MRI, plays a vital role in improving health outcomes by giving doctors the tools they need to see the inside. And how does it work? We use the inverse Fourier transform to transform a signal into an image, and in this case, a cardiomagnetic image. We have some examples here. At first, the whole body of the man and a woman, and also we can capture the movement of the velocity of the blood with cardiomagnetic images. We use some images processing to obtain, for example, the whole body, finite elements, a grid, and then we can interpol the velocity data in order to obtain the video in the abstract. Also, we have some examples of brain magnetic resonance imaging. We have several segments. For example, anatomic images such as T1, T2, and proton density, and also have some structural features. For example, spectroscopy, functional diffusion, and for more detail, we're going to talk about today about susceptibility. Here we have an example of spectroscopy. MRI spectroscopy analyzes the chemical compositions of tissue by detecting metabolites, providing insights into cellular activity. Also, we have some examples with functional MRI, also known by fMRI, magnetic brain activity by measuring change in the blood flow, revealing which areas are activated during a specific task. And then I'm going to talk about my work that is titled Interpretable Magnetic Machine Learning Model for Characterizing Magnetic Susceptibility-based Biomarkers in First-Episode Psychosis. So we have neurological alterations in deep brain nuclear psychosis patients. And as you can see, these 22 deep brain nucleus are in the GIF in the right on the PPT slides. These have dopaminergic dysfunctions in subcortical areas. And quantitative susceptibility mapping, also known as QSM imaging, quantifies changes in brain magnetic susceptibility, iron concentrations, and cofactor into dopaminergic pathways of neurons. So the aims of the works is to identify predictive QSM and R2 star biomarkers in first-episode psychosis patients and their response to antipsychotics. So the methodology consists in this summary schematic description of the registration process. First, we changes the resolution of the atlas into the standard space, also called M&M. Then, second, we co-register the 2-1 weighted gradient echo and the magnitude multi-echo of the gradient echo image. Third, T1 was normalized and the deformation field was obtained, and then we apply the deformation field to the QSM and R2 maps, normalizing them into the MN1 space. Finally, we multiply the atlas with the QSM and R2 start maps in each subspace to obtain 22 mean magnetic susceptibility values per map and the same number of the mean of R21 values. So, the machine learning strategy consists in developing two machine learning models to analyze the brain regions of the QSM and R21 values. Distinguish between healthy volunteers and first-episode psychosis patients. Responders, also called RS, and treatment-resistant patients, also called TRS. The models were built using Python and employed in random forest with sequential forward selection, also called SFS, for feature selection. Then we hyperparameter optimization through grid search using tenfold cross-validations. Finally, we use chat values for model interpretation, revealing feature importance. The demographic and clinical data were separated in mostly three groups. The first one is called the healthy volunteers, consists of 61 subjects. Then we have a big subgroup called first-episode psychosis patients that consists of 76 patients. And also we can divide them in two groups called responder psychosis in 52 patients and treatment-resistant psychosis in 21. So the machine learning results we have here with healthy volunteers and first-episode psychosis classes. We obtain 4 features: right nucleus accumbens with R2 start, left amygdala with R2 start, left nucleus accumbens with R2 start, and right thalamus with QSM, yielded accuracy of 66.5 approximately, with a deviation standard of 10.6% for accuracy. Using the grid research with selection forward selection SPS for random forest. Then we have also another result with resistant schizophrenic and treatment-resistant schizophrenic. We obtain 4 features that they are right hippocampus and R21, left caudate and R2 start, and left putamen and RF2 start, and left amygdala and QSM achieve an accuracy of 66 with a deviation standard around 30%. We have some results values with the CHAP values, and then after applying the feature selection, we use 3-CHAP analysis was conducted to identify the most important prediction in the model as shown in the figure. The CHAP summary plots show that the key features of the healthy volunteers and the first episode patients classification were the right nucleus accumbens and R2 start, the left amygdala and R2 start, the left nucleus accumbens and R2 start, and the right thalamus with QSM. For the classes of the resistant psychosis and treatment-resistant psychosis, we have the important features were the left amygdala and QSM, the left caudate and R2 start, the right hippocampus and R2 start, and the left putamen and the R2 start. Both classifications use similar features, leading to confusion between classes. The CHAP values indicate the contribution of each features to the model predictions, with lower right nucleus accumbens in R2 start values increasing the likelihood of being classified as first-episode psychosis patients. At the same time, higher left amygdala with R2 start values favor the healthy volunteers classifications. Finally, here we have some results that discriminating brain regions according to 3-CHAP per map. We have a rendering 3D with both classification tasks, A with the healthy volunteers and first episode psychosis, and B with the subgroups of the third class. We have a 3D rendering and the axial plane of selected regions for QSM and R2 stars maps. In conclusions, iron roles in brain function. Iron is crucial for dopamine synthesis, but excessive iron accumulations is linked to brain pathologies, especially in psychosis. And the machine learning approach for classification we can obtain the random forest models indicate that the key brain regions, deep gray nuclei, were altered in QSM and R2 star values, distinguished between the healthy and the first episode psychosis patients and treatment-resistant schizophrenia, and combining the QSM and R2 stars overperforms integrated emergence in classification tasks. The interpretability with CHAP values lead us to highlight that key regions like, for example, amygdala, nucleus accumbens, thalamus, influencing classifications. Higher R2 stars values in left amygdalas and nucleus accumbens for first episode psychosis patients and lowers in the right thalamus nucleus in accumbens for healthy volunteers. As we have some challenges and variability. High standard deviation in our model indicates the sensitivity of the data imbalance. We have to recall that we use 10-4 stratified cross-validation that lead us to these results. And advanced oversampling techniques, for example, cross modes, are needed to improve more robustness of the model. We have some future directions that expand the dataset size and explore deep learning models and use techniques like extrapolation to improve the classification and paramagnetic and diamagnetic components. Well, thanks for your attention. You have an email for future collaboration if you want. Thanks to everyone and have a nice day.